Good morning. Welcome back. So, um, like I said in the announcement last night, this assignment's taking a little bit longer to mark just because the trees are big, and it'll be the same thing for test two, unfortunately, and the same thing for assignment five, just because there are trees on those and they do take a while. So I hope you've had some time to look at the answer key or at least skim it. And if so, are there any questions that any of you have about the answers or about how to solve these problems? Since I'm sure you've seen the test two guide and um, you do have to do a tree on there. So figured if you have questions, we can take some time to go over those for Friday.
I have a question about the last question.
The last, so question five.
Yeah, so the V bar, does it take the direct object first or the indirect object?
In this case, what was the sentence? So the sentence is, uh, so I showed Carol the Hunchback of Notre Dame. This is the equivalent. So the direct object is the thing that you're giving. So in this case, it's taking the indirect object first. But if you have another paraphrase of this, since I mean, there's two ways to do this. The one I gave you was the paraphrase where the indirect object is first, but we can have a version of the sentence where um, there's like a prepositional phrase here. We just don't know how to deal with prepositional phrases yet, so that's why we're using um, this version. So in this version, you would have a direct object first. But in order to do the indirect object second, we need to know how to deal with prepositional phrases. So this is assignment, not five, maybe six, maybe. I don't know if we'll do this, but that's a possibility. So for this one was the indirect object first. But even though you're doing the indirect object first, in the X, Y, Z pairs, it's just about the order that they show up. So you're filling in the second position first, whether you're doing the direct object first in this tree or the indirect object first in the tree that you drew for the assignment. It's the second position. So the Y is filled first. And then when you get to the VP, then you're filling in that the Z position. But in the VP, you're just looking at pairs XZ and you're filling in Z.
If what I wrote is different from that, but the rule still makes sense, would I get part marks?
Yeah, so I'm giving part marks for your rule attempts here. As long as it's somewhat close, you're getting at least 50% for the rule. And even if your rules don't work, you drew a syntactic tree for it and you applied the rules. So I'm not gonna like penalize you twice for it. I'm just gonna assume that your rules work on the tree and then check to see if there's other problems with the tree. Um, so whatever you wrote for B and C, I'm just going to assume works for D when you do it. Okay. Were there any other questions? And for the test specifically, you will need things like questions 1 and 2. But the questions about 3, 4, and 5 are okay too. Okay, I just want to reiterate that on Friday, I am giving you the structure for the tree, so you don't need to figure out the structure. You don't need to draw it. And I'm also telling you like a list of all the different nodes, so you know exactly which nodes you have to give things for. I mean, which is everything. But if you're wanting to write it out in list notation instead of just on the tree, you can just write A, B, C, D, E, F, G, and however many there are, just to save some time. Okay. if we're good with that, we can always come back to it at the end of the lecture if you have questions. That's not what I wanted to do. I forgot. This is on the program, not on OBS. So last time we did some translations. Let me do that. So we did these translations. It's a little bit messy with some of the things we wrote here. But basically with these translations, what we looked at in 15 and 16, we're translating according to truth. So everything is hot or everything is cold versus everything is hot or cold. What are the restrictions for truth there? In 17, we introduced how to do noun phrases with adjectives involved. So by using the conjunction to join the adjective and noun together. Also like the hidden quantifier here with tall trees. And then in 18, we talked about at least one, and then another example with a noun phrase with an adjective involved. So now your job is to do some practice. And some of these are equivalent to the things that you've seen before. Some of these are a little bit simpler, but just because it's simpler doesn't mean it's any easier, because when you see more difficult things, you want to take the simpler things and make them more difficult as well. So for A and B, try not to overthink these ones. E is ambiguous. So this one has two translations. It's scope ambiguous, to be specific. And then F is, well, this one is difficult. So I'd like to give you some time to try to work these out. About 8 minutes or so. We can do F together because F is a bit of work, but if you do finish the other ones in the 8 minutes, feel free to try those on your own, but F is quite tough. So I'll put 8 minutes on the clock. If you have any questions while you're doing them, feel free to ask, but yeah, if you do finish early, you can, I guess there's no real way to put these in chat, which is unfortunate. But if you can figure out a way to put these in chat, then that's another fantastic way to demonstrate and to submit your answers so I can see if you got them right or not. It looks like the timer has stopped at 30 seconds. I don't know how long it's been stopped at 30 seconds. Um, anyways, I'll talk about things. So hopefully you've had a chance to attempt them, since the best way to practice is to attempt and then get immediate feedback. So, 19A, John likes Susan. The reason this is here is because often when you see all these different extractions of NPs, you tend to overcomplicate things. But John and Susan are proper names. And when you have proper names, we just put them directly into the predicate, because these are individuals in our world and we can evaluate them directly. So John likes Susan, we can just translate directly as likes John Susan. And then we know whether that's true or false in our world. So that's the translation for John likes Susan. If we compare it to something like John has a cat, we know that a cat is a noun phrase. It's so it's an existential, so we'd pull it out. And if we want to paraphrase it, we can paraphrase it. So we can say like, a cat, John has X, so there exists an X. I won't keep that on screen because it'll just get muddy, but we can say there exists an X such that X is a cat, or exists an X, cat X, and has, so John has a cat, John has X. So John has that cat. And again, we use X here to represent the cat because we've established X as being a cat before. So that X is just pointing back to that cat. So yeah, A is just likes John Susan. With proper names, we don't establish some predicate. Whenever we use a quantifier like exists or for all, we're saying some or all. So if we were to do something like say, there is some X such that X is John, then we're saying some John likes Susan. But we don't want to do that. We want that particular person, John. So likes John Susan is all we need. Okay, the next one, barking dogs don't bite. I gave you a paraphrase of this. Just because barking dogs, I mean, we have this ing here, which looks a little bit different from an adjective, but we can just treat it as an adjective here. So barking dogs, every dog that barks doesn't bite. Okay, so we could pull this out and get all barking dogs, X doesn't bite. So let me do C, and then we'll jump back to the question about A. So all barking dogs. So for all X, if X is a dog and X barks, so this bit here, dog X and bark X, just says barking dogs. So all dogs that bark. We could do dog X and barking X, or dog X and bark X, or dog X and barks X. I don't really care about the tense of this verb-like thing. It's an adjective. That's fine. Doesn't really matter to me what it is. It gets the point across. Then doesn't bite. So not bite X. So again, even though we're in predicate logic, so we can use the negation symbol. We don't want to say not bite, we want to use the negation symbol. So for all X, if X is a dog and X barks, then it's not the case that X bites. Okay, so this is like the same thing that spooky ghosts don't bite. Same thing. Spooky ghosts don't bite, barking dogs don't bite. It's just instead of spooky, we have this thing that's in ing form. Okay, what if it was John likes a Susan? Would it be existential in that case? Yeah, if it's John likes a Susan, we could say it's existential. So if we have, yeah, John likes a Susan, then we could do something like there exists an X such that X is a Susan and likes John X. So in that case, you're ascribing the property of being a Susan to some individual. It's a little bit weird, but it can work. I think in the modern day, maybe this would be a better interpretation if we change it to something like John likes a Karen. Maybe this interpretation is a little bit more well, less awkward English and more understandable. But yeah, John likes a Karen. There exists an X that X is a Karen and John likes X. But if it's just a proper name, we want them as constants within the predicate. Okay. So D, either every fruit is bitter or every fruit is sweet. This is very similar to the one I did earlier with the hot or cold. So we translate every fruit is bitter, we translate every fruit is sweet, and then we put an or between them. So we can use the same variables or different variables, it doesn't matter. Let's just use some weird variables just so we get used to seeing some weird variables. So let's do something weird. Let's say for all P, why not? Instead of X and Y, let's use something different. So for all P, if P is a fruit, then P is bitter. Or, so that's every fruit is bitter, or every fruit is sweet. So let's use something, I don't know, like for all S, a capital S, why not? For all S, if S is a fruit, then S is sweet. So that would say, or every fruit is sweet. So this is our translation of either every fruit is bitter or every fruit is sweet. So normally we can just use X and Y, but sometimes you see these weird things with different variables. They can all be used. Okay, I just want to make this a little bit smaller. That's too small. That's unreadable. Hello? Okay, technology is crazy. E, every student heard some news. So this is scope ambiguous, meaning that if we say that every student is X and some news is Y, our translation and interpretation depends on which one we pull out to the front. So basically we can get every student some news, or we can get some news and every student. And these have two different meanings. So this sentence has two different translations. So we want to make sure that we get both. So we can do one case where we pull out student first, or student to the very front. So for all X, if X is a student, then we use the arrow. And now we're going to do some news. So this is every student, and now we'll do some news. So we'll say there exists a Y such that Y is news, and because we're dealing with the existential, and what's our predicate here? So heard. And who's hearing what? So the order here matters. The students are hearing the news. So X is the student, Y is the news. So X is hearing Y. So for all X, if X is a student, then there exists a Y such that Y is news and X heard Y. So to remind you of which interpretation this is the case where first we focus on the fact on, well, first we focus on every student, and we're saying that some student heard, or every student heard some news or other. So this is the students and this is the news. So it's not some particular news, it's just every student first, and each student heard some piece of news. It can be different pieces of news. Okay, With the other translation, we're just flipping which noun phrase is to the left. So we're going to do some news out front, and then every news is further inside. So I'll do this in a different color. You do this in red. So we'll say first there exists a y. I like to keep the variables the same between both translations just so I don't get confused, but you could start with exists in x if you want, and then do news as x. But sometimes that gets a little bit confusing in your head if you're keeping track of what you've done. So we'll say exists in news y, and because we have the existential, we're going to use and for all x. If x is a student, then okay, we're going to do heard again. And who's hearing what? Well, again, x is the student. Oh, sorry. I missed the predicate there. Student is x. And then x heard y. So the student hears the news. Okay. And then this translation, the second one, is the translation where there's some particular news. So there exists a y such that y is news. And then every student heard that news. So this is that second translation where the existential scopes over the universal. So 2 translations for that sentence. Okay, before I do F, I'm going to do F on a separate page just because I need some room to write. So I want to make sure that if you need to copy stuff down, you can copy it down. But are there any questions about A through E? For D, does there have to be 2 variables? No, we could use the same variable if we want. It would be totally okay for us to use P as well. In this case, that would be fine. Because they have different scopes, so we can reuse them. Okay, so if you didn't struggle on A, B, C, D, or E, you might have struggled a little bit with F. And the reason why F is tough is because of this word any. So this is a sentence with something called a negative polarity index or a negative polarity item, NPIs. So whenever you have negative quantifiers like no, you need to use different quantifiers down the road. So any is one of those words that we use with negative quantifiers higher in the sentence. So when we think about the interpretation of this sentence, no student likes any exams, we can do our mechanical approach fairly well up to a point. So we know how to do extraction. So we can do X and Y here. We can extract them out. In fact, it isn't clear at this point, but there's really only one interpretation here. This isn't scope ambiguous, and that's not clear at the beginning because of this word any. So I'm going to pull no student out to the front. So we'll say no student X, any exams Y. So we'll go formulaic as far as we can. X likes Y. Okay, so no student is nice. We can translate no student. We know that no is there does not exist an X. So no is the same thing as not some, like there is no student out there. There's not at least one student out there. So there is no X such that X is a student. And so now we have to deal with any exams. And the question usually is, well, what is any? Is any a universal or is any an existential? And just out of like intuition, or if you've worked it out, do you think this is an existential or a universal?
Should it be a negative universal?
A negative universal. I mean, if we do a negative universal, that's really going to work out to be an existential in the end. So by saying negative universal, you can say existential. So uh, yeah, I mean, that's what it's going to end up in the end. And so a little trick for this, if you're wondering, like, is it a universal or an existential, is to think about a paraphrase with the universal and to try to simplify this. So is this the same thing as saying no student likes all exams? Is no student likes any exams the same thing as saying that no student likes all exams? And if you think about this, well, if a student in this case, let's say there's 3 exams and they liked 1 and 3, but they didn't like 2, well, this sentence would be true because they don't like all the exams. They just like some of the exams. But if we think about the sentence, no student likes any exams, well, this should be false because they like exams 1 and 3. So really, our best translation here would be the existential, because they shouldn't like any of those exams at all. So the universal really isn't, like the universal with this paraphrase really doesn't match our intuition of what should be happening. If we have this situation, the sentence, no student likes any exams, really shouldn't be true. It should be false. And that's what we're going for. So like universal is bad here. So some of you intuitively might get any exams as an existential a little bit faster, or like a negative universal. That's another way of thinking about it. The other way here is to go a little bit more with the paraphrase and think, well, what if it was a universal? What could we do to figure this out? Okay, so we're just going to translate any as an existential by sort of working it out this way and saying, well, what do we need for the sentence to be true? So we'll just say exists a y, exam y, and carry on with our translation. And then likes xy. And then that would be the end of it. So now here's the thing though. Like, okay, well, okay, Trevor, you just worked out some situation. You said, okay, this is the existential. You translated it fast, and then you say you're done. Well, we should still check to make sure that this translation makes sense when we read it out loud. So there is no X such that X is a student. So there's no student. And so there's no student. And there's some exam, Y, and X likes Y. So in other words, there's no student X and some exam Y where that student likes Y. So this is really what we want. There's no student out there where there's some exam and that student likes the exam, which is what we want. If we also just sort of section this off and think, okay, what does this say without this negation up front? There's a student that likes some exam. There exists an X such that X is a student. There exists a Y such that Y is an exam, and X likes Y. So some student likes some exam. If we negate that, then we're saying there's no student that likes some exam, which is the same thing as saying that no student likes any exam, which is exactly what we want. Sorry, go ahead.
Sorry, can you put the bracket between student and exam instead of student and, like, can you shift around?
Um, sorry, the brackets.
The
I
square
mean,
brackets.
you can flip the order of the student and the exam. I'm just putting the brackets here for scope purposes. If I don't know if this is what you mean, but you can also do something like this. Something like that would also be fine.
Okay, thank you.
Like there is no X and Y where X is a student and Y is an exam and X likes Y. That'd be another way of paraphrasing not paraphrasing the sentence, but paraphrasing the translation or finding an equivalent translation. And the only reason we can do this, by the way, is because they're both existentials. And existentials are special because they're all joined by conjunctions. And because they're all joined by conjunctions, you can move things around as you want. It's all free movement. And because you have all this free movement, we can just sort of slide everything to the front. This is a special case where you can just move everything up front. Okay, so I mean, this was a tough translation. Typically, you don't, or I don't have you do these tough translations on your own, but it's a nice thing to talk about because it does relate to things as NPIs, which you will see in link 322, maybe? I don't remember for sure, but I think that word does come up in 322, either in an exam or in some assignment. So it's a nice little tie into that course. Okay, so are there any questions about predicate logic translations? Check. I think on assignment 5, you'll have some more practice. Well, obviously, and on the lecture page itself, I believe there's some more practice. So on the lecture page on Canvas, from where are you? There is 8 more here. So, oh, no student likes any exams. There's some. Oh, these are very similar. Okay. I'll find some more resources with some more practice for you that are not just these ones. But there's many resources that use different symbols, so I'm always hesitant to give you resources that use different symbols, but I will try to find some more practice exercises with translations as well for you with predicate logic. But the ones I give you on the assignment, I try to make quite similar to the ones in class. Okay. So before the break, I just want to talk now about assignment functions. So assignment functions are going to allow us to figure out what variables are, what pronouns refer to. So what we've been dealing with our translation so far have not really included pronouns. Because when I said, when we have a sentence like he sleeps, well, we take something like he, we don't really know what he is. So we have to treat this as a variable x. We get a translation like sleeps x. We say, okay, this is an open formula, but we can't really evaluate it because we don't know what x is. We don't know who x is. All we know is that x is he, but we need some sort of context. And what an assignment function does is an assignment function gives us context. It just gives us context in a way that's very mathematical. So it defines what our variables are. So that way, if we get to the end of a translation and our variables haven't been bound, or our variables haven't been replaced by constants, then we know who our variables are in the real world. So an assignment function is just a function. So we have a function g. Typically, we use g for assignment functions. And we take variables, so usually x1, x2, and x3, and we assign them constants. So we take our variables and we assign them to people. Okay, so here's how we can establish the assignment function. We could do it in formal notation. So we can say our assignment function g of x1, so this is a variable. Yeah, this is on Canvas. This is in the predicate logic slides on Canvas. This page is published, right? Yeah, it's published. Yes, yes, okay. This is slide 20, yes. Okay, so we can establish it with function notation. So we can say g of x1 is John, and we could say g of x2 is Mary, and g of x whatever is Pete. But remember what we said about functions is that whenever you have a domain, everything in the domain has to be mapped to something. And in this case, our domain is like all of the possible numbers. So what we do is usually we cheat a little bit and we say, okay, the last thing is going to be xn. And we're going to say here is that n for any number greater than whatever that last thing is. So this really should be 3 if we're continuing our count, but we only have 3 people that we're talking about. So we don't want to say that x3 is Pete and x4 is Pete and x5 is Pete, because we got to do like an infinite number of these, because we have technically an infinite number of variables that we have to map just by the definition of what a function is. We cheat. So we say, okay, xn is going to be Pete for every n greater or equal to 3. So it's just a way to satisfy the needs of a function without writing out a bunch of variables. So we can do it like that, or we can write it out in a nice matrix notation. So just like we did in our trees with truth values, we can write it out like that for functions as well. Okay, so now if we say something like, let's look back at this he sleeps example. If we say something like he 4 sleeps, so we give this an index, he 4 sleeps. Well, now we know that in our translation, we should be using the variable x4 sleeps. So when we translate this into logic, we'd say, okay, this is sleeps x4. Okay, we don't know who x4 is. x4 is a variable, but now we have context. So we can check our context and we can say, okay, well, who is x4? Well, this one says x3, x4, x5, everything after x3 is Pete. So in our translation, we know really that this is saying that Pete sleeps. So now we know who he is. The assignment function has told us who he is. Now, the assignment function is something that we establish. So we know what the context is. We feed the context to the math. And then the math just allows the system to do its thing. So, like how does the math know what the context is? Well, we provide it with the context. This is just a system that allows us to give it context. Okay, so now we can not only translate variables and pronouns, but we can say who the pronouns refer to in the real world. The only thing that this doesn't do, and this, depending on what your take is as a syntactician or semanticist, this can be either a strength or a weakness of the system, uh, is that the pronoun itself doesn't really care about the gender of the proper name that it refers to. So if you do something like he too sleeps, like he with the index 2, well, x2 is Mary, so he sleeps with a 2 would be Mary sleeps. So if that's a problem, then that's a problem. If it's not a problem, it's not a problem. Our system doesn't care. You could create restrictions on the assignment functions to say that the gender has to match or the gender can't be different. Our system doesn't matter. Okay, so here is the system that we had on the last slide. So this was our original assignment function with x1, x2, and xn. Now, we can replace things in our assignment function. So we use this notation, g with d/v. And what this means, and this is a very cumbersome notation, so here's an alternative way of writing it, and you can use this if you want. This says G, where V now points to D. So this means that D is replacing whatever V originally pointed to. Or alternatively, D replaces whatever V pointed to originally. So that's how you can think of it. And I've just shown 2 examples here because I think actually seeing it is probably the best way of actually understanding this notation, because the notation is not really that pretty. Well, when I say it's not pretty, I mean it's not really intuitive. So for example, let's say we take G1 and we do this replacement. We say Rufus/x2. What this means is that we're taking our original assignment function and whatever was in x2, we're now replacing with Rufus. So x2 used to be pointing to Mary, as we see originally, but now we've replaced Mary with Rufus. So it's like a substitution. So maybe someone leaves the conversation and comes in, so we make an adjustment to our assignment function. Okay. We can do multiple substitutions. That's fine as well. So here's a case where we have G1, Mary replaces whatever was in X1, and then Rufus replaces whatever was in X2. And what I should say is inside brackets first. So Mary does the first replacement at X1, and then Rufus does the second replacement with X2. And we could do this on and on and on and do however many replacements you want. So with a concrete example in a sentence, we're going to take a look at the original assignment function. So this is G1 up top, or just G, where we have X1 going to John and X2 to Mary and Xn to Pete. We have the sentence, he is happy. So he 3 is happy. So if we translate this into predicate logic, it's happy X3. We're just using the regular assignment function. So we know that X3 is Pete. So this means that Pete is happy. But if we take that same sentence and we do a modification, so what we're doing is we're taking our assignment function G1 and we're replacing X3 with Sam. So we translate that again to happy X3. We're still replacing Sam with X3. Well, now when we do our predicate logic to English, we now have that Sam is happy instead of Pete, because we've done a replacement where X3 now points to Sam instead of Pete. So the English sentence changes as well. Okay, are there any questions about these assignment functions before our break here? What is the superscript M in the example? Yes, okay. I was going to talk about that in a bit, but I guess because the question came up now, we can talk about that now. Before, we just used V to talk about a situation. Now, because we have assignment functions, what we're doing is we're changing it to M and G. So M is a model. So M is pretty much just like a situation, but M encompasses the situation and the assignment function. So M really just allows us to write a little bit more. It just says that there's a little bit more involved in our universe than V. So you can just think of it as a change of variables for now. So we're just getting a little bit more information in what we have to evaluate our sentences and our predicate logic translations. Okay, so why don't we take a 10-minute break and then we'll come back and then we'll do the last few slides of this lecture. So I'll see you in 10 minutes. Okay, just a few more today. So by the way, we're not finishing the entire lecture set for predicate logic. We're only doing up to slide 25. 26 through 30 are there. When topics like tense and time and jokes and pragmatics are not included in the course, but because those two lectures are, there's less focus on proofs. So we're just doing up to 25 today and in this course. So the rest of this is about evaluating predicate logic formulas as being true or false and looking at equivalent translations. So we're going to talk about assignment functions a little bit more in semantics. So if you do have any questions about them, please feel free to interrupt me. So this slide is a little bit technical, but let me just go through this a little bit more casually. So this is about how we interpret our predicate logic formulas. So we have these superscripts M and G. So M is a model, and we still use V as a situation. So V is a function that evaluates whatever our constants or terms or predicates are. And then we have the assignment function G that tells us what our variables are doing. So now instead of having a V up here, instead we have an M and G. So what A and B are doing, so what A says, if alpha is a constant, then the meaning of alpha is just whatever alpha is in the real world. So what this says is if you have something like John, then it's going to be the individual in the real world. So this would be J prime. If you have alpha as a variable and alpha is in the assignment function for B, so if you have something like x3, I really should be putting M and G in the top right of each of these. Then we take a look at our assignment function and we ask ourselves, what is the assignment function doing? So maybe we take a look at G and it says, okay, x3 is pointing to J prime. Then we'd say, okay, this is J prime. So what A and B are saying here is that our constants and our constants and our variables, we just evaluate our constants and predicates, our constants and variables as before. If P is a predicate, so if you have something like likes, then it's just evaluated as a set. So this is just like before. If we have likes, then we're going to be taking a look at a pair XY, where X likes Y, but now instead of being in some situation V, we're now in a model M. So slight difference there. Instead of being in a situation, we're now in a model. And a model, I guess I really should explain what a model is in more terms. A model is just like a situation. It's some construction of a world. It's some hypothetical world that we're constructing. Okay. And of course, with the predicate, depending on if it's intransitive, transitive, ditransitive, or if it's a word like range that has no variables, that'll depend on, of course, if whether you're looking at pairs or triplets or singletons or just the empty set. Okay. Now taking these 2 points together, we can say whether something is true or not. So for instance, imagine we have something like likes, and then we have, say, John and Mary. And we want to know whether this is true or not. So the sentence, John likes Mary. With predicate logic, how this works. We say it's true if our pair here is in the set. So when we do a tree structure, we break things up into, how the tree is formed. But with predicate logic, we're just taking a look at the pair itself. So this is going to be true if John and Mary is an element of this set. So an element of the set of pairs XY such that X likes Y in M. So a little bit different than how we did our trees, but this is just the difference between predicate logic and how syntacticians and semanticists do trees in linguistics. But of course, if we had a intransitive verb like sleeps, you'd just be saying, well, if John sleeps is true, then just John is in the set of X such that X sleeps. With a ditransitive verb, you'd be looking at triplets in a set of triplets. So that's what this represents here. If you have P with, let's say, n terms, and you're looking at an n tuplet being in that predicate. But we're not going to mess too much with the theory here. We're just doing the application of it. Okay. Yeah, so I mean this is the bulk of the complicated notation. So if you remember set theory and relations, then you're good here. Not much has changed. Just a different notation for the theory. As far as the connectives, everything is the same for not alpha, alpha and beta, alpha or beta, alpha arrow beta, alpha if and only if beta. It's exactly the same. Yeah, it's a lot of words. It's just, new system. You got to make sure that everything is formally explained. What's different is this stuff. And this is where the assignment functions come in. In fact, I think let's just do this on a separate page, just so we're not muddying up the screen with the other stuff. So the connectives are going to be exactly the same, so let's not focus on that stuff. Okay, so A says for all V alpha. Okay, so if for all X alpha is true, for all X alpha is true. Okay, how do we know that some formula is true? So alpha, we don't care exactly what is an alpha. There could be stuff that's bound in there or stuff that's not bound in there. If it's true, basically whatever is bound in there, the formulas have to be true for every single replacement. So let me just write this out again. So it's true if alpha in the model and in the function where x points to d, so we're making a replacement here. So this is a replacement, is true for all d in the universe. Okay, so I'll just write this out first and then I'll explain this again. Okay, so I'm using x instead of v here just because we've seen x before. Okay, I should also be using double brackets here. Okay, I want to use a concrete example here too. So let's say we have for all x, rxx. Okay, so, and then in our universe, let's just say we have a and b. Okay, if I want to know if for all x, rxx is true, what this means is I have to go through everything in the universe and I have to see if rxx replaced by all the variables in the universe is true. So I need to check to see if RAA is true, and I need to see if RBB is true. And if all of these things are true, then I can claim that for all x, rxx is true, because I'm saying for every x, rxx is true. So that is what this is saying up top. For all x, alpha is true if alpha, where I replace x with d, is true for all d in our universe. Well, d is just a variable. So what d is doing is it's essentially running through everything in our universe. It's replacing x with everything in our universe, and it's just checking all different possible combinations. So for RXX, it's checking A. It's saying, okay, is RAA true? It's checking B. Is RBB true? Once it's gone through everything in our universe, it says, okay, are all of those combinations true? If so, then for all X, RXX is true. The existential is similar to this, but with the existential, if we do something like exists in X, RXX, it functions the same way. However, it only needs to be for some individual. So for instance, RAA can be true, but RBB can be false. But because there's just at least one true, we're good. Because the difference between for all and existential is for all says for all individuals, while the existential just says for some individual. So the difference between the universal and the existential is that the universal has to check everything and they all have to be true. The existential checks everything, but just at least one of those has to be true. So again, the notation is a little bit cumbersome, but the actual application is you just check, all the different constants in the universe and you check to see, okay. It's like if I say everyone likes chocolate. Well, I have to check everyone in the universe to see if everyone likes chocolate. If everyone likes chocolate, it's true. But if someone doesn't, it's not true. If I say someone likes chocolate, then I just have to find one person that likes chocolate. I can check everyone, but as long as one person likes chocolate, we're okay. So I can actually just write this out. The bottom part is hidden. I don't think there's anything where I am. But there's nothing, there shouldn't be anything hidden on the screen. I can unwebcamify myself, but here's what happens if I scroll up. Oh, it was the black bar of Zoom. Oh, okay, sorry, my bad. Okay. So although the notation is a little bit cumbersome, we will see this notation in our trees in the truth conditional meaning of quantified sentences lecture, but we will go over that again when we see it. So just, uh, you know, um, what am I looking for? The words in my head. Familiarize yourself with with what it looks like, but don't worry about it too much right now. Just look at it and understand what it means, but don't worry about writing it at this point. We'll reintroduce it again when we see it. Okay. What's more important right now is the application of these. So are there any questions about really this concept and understanding how to check for the universal and the existential? Okay. There's one last point here. So because quantifiers bind variables, quantifiers can modify the assignment. So this is really what this process is. When you do the assignment function replacement, this is how we do binding. So it might not seem like that because, we're just replacing a variable in an assignment function. Um, but if we think about, say, a tree, just sort of drawing this out quick. If we do a replacement on a variable and we do something like, let's say x to a here, or let's do the other notation, a to x. What we're really doing is we're replacing all of these x's with a's. So what we're really doing here is we're binding all of those x's. All of this is in the scope, it's C commanding it. So these variables are no longer free. We're changing them. We're binding it. So this is the process of binding this assignment function. So um, it doesn't seem like it's very powerful at first, but this is the process of binding. That's why when we do truth conditional meaning of quantified sentences next week, we're going to see this again. Okay, so let's do some practice here. We have a model, so this is the information we had before, but we've converted it into just predicates. So what we have is a universe. So we have three things in our universe. We have A, we have B, we have C. We have some predicate A. We don't know what A means, but A is in the predicate and B is in the predicate. We have another predicate R that's pairs. So A is related to B, A is related to C, C is related to B, and C is related to C. Again, who knows what R means? And we're asked to determine the truth values of the following formulas. So we're using the same propositional logic things with our connectives. And we're also having to check the truth values of the predicates themselves. So I'll do like A with you, and then I'll let you do B, C, D, and I'll do E with you as well. So I'll do A and E, and then I'll let you try B, C, and D on your own. But so for example, A, we need to check the truth value of RAB and RBB. So what we do is we check to see, okay, first we ask ourselves, is RAB, so for RAB, is AB the pair in R? So yeah, we see AB in R. So we know the first one is 1. That's true. RAB is true. But what about RBB? We have to check to see if BB, the pair BB, is in R. Well, I don't see BB in R, so that's going to be false. Therefore, the entire formula here is going to be false. RAB and RBB is false. So again, the same truth value rules for the conjunction here. The bottom one I'll do with you just because it's a little bit more complicated. Exists a x, exists a y, exists a z, such that rxy and ay and rxz and not az. Oh, okay. So basically what E is saying, this is a big jump, is that there's some x and some y and some z where all of these 4 things come out to be true. So can we find a replacement for x, a replacement for y, and a replacement for z that makes all of those things true? And when you get something like this, sometimes it's just trial and error. So what I noticed right away is not AZ. So not AZ means that if I find something that's not in A, then it'll come out to be true. So I have A and B in A, So if I take Z and I replace it with C, then this will come out as true. Since AC is false, so not AC will be true. So if I replace all my Z's with C's, then I have something that's true. Okay, so now I have R blank C. Well, what's with C that would make that true? Well, I have AC and I have CC. So I could use the same letter. I might use a different one. So let's say, okay, let's pick A for X. Okay, I'm going to pick A for all of my X's. And I have A and something. So let's try, I don't know, let's try B for Y and let's see what happens. AB and RAC and not AC. Okay, so I have RAB, that's true. I have AB, that's true, because I have B and A. I have AC and R, that's true, and not AC. Well, C is not an A, so that's true. Okay, so I can find one combination that makes all of these true. Therefore, I can say that this whole well-formed formula is true. So that one is a little bit more difficult because we're saying, oh, there exists some combination of X, Y, and Z that make all of those true. So we have to do some testing. And sometimes you just have to keep plugging away in and trying out different variables to see if there is some pattern that works. But luckily, we could kind of reverse engineer this one. So feel free to try out B, C, and D on your own. I'll give you a few minutes, so 4 minutes or so to try this out, and then we can go over the answers. If you have any questions, as always, interrupt me at any time over chat or voice, and I'm happy to answer those. Put that right there. Remember, for the universal, you have to check everything in the universe. So the universe is A, B, and C. Okay. I hit some buttons on Zoom. I don't have to ask if you can hear me because the captioner is captioning my words. Right, I fixed it. Um, okay, so B, not AC, arrow RAC. This is a good test to see if you can remember how the conditional works. So not AC. So if AC is 0, because C is not in the list for A, then not AC is 1. So here we have a 1 arrow RAC. So is AC in R? Yeah, AC is an R in there. So we have 1 arrow 1 in this case, which says this one is true. Okay, for C, I want to ask you all this. Is C true or false?
False.
It's false. So for all X, RXX, you have to check everything in the universe. So we have A, B, and C. So we have to check RAA, RBB, and RCC. So RAA, there is no AA. So at this point, we could just stop because we have to check, we have to see that all of those are in our universe, or all of those are true. But we don't have RAA, so we can just say that's false. We don't have to keep checking. If you want to keep checking, you can. You'll find there's no RBB, but there is RCC. So what you could say then is that there exists an X, RXX. That one's true, but for all X, RXX, that one is false. Okay, this next one is interesting. So for all X, RXX, if and only if, not AX. What did we get for this one? Is that one true or false?
True.
That one's true. Okay, so let me actually do this one here. So for this one, not AX. So then we had to check not AA. Sorry, this should be a little bit neater when I do this. Not AB, not AC. So because this is the biconditional, we have to check the values of each one. So we know that this is 0, 0, and I'm going to do 1 in blue. So now we have to check not AA. So we know that AA is true, so not AA is false. AB is true, so not AB is false. And then we've known from before doing them that not AC will be true. So actually, all of these, because the biconditional is true when they're the same, each of these are going to be true. So because all of those are true, for all X, RXX, if and only if not AX, is going to be true. So D is actually a true statement. For everything in our universe, RXX is the same thing as not AX, or has the same value as not AX. So this is how we evaluate the truth of different formulas relative to a model.
What happens if one of the lines turn out to be like 0, 1 or 1, 0?
So if you have 1, 0 in that case, like if you have 1 if and only if 0, then you would get false overall because they're not the same value, and then the whole thing would be false because there's at least one that is not true.
Okay, thank you.
Okay, are there any questions about evaluating these types of predicates? I'm just checking assignment 5, which I have posted during the break. On assignment 5, you will have to do something very similar to this. And there's also something with an equal sign. So I just want to do something with an equal sign here. Just for practice. So if I say something like there exists an X, such that a X or X equals A, sometimes we can have formulas that look like this, and we touched on them very briefly at the beginning. But basically, what this is saying in this case is that there is an X such that X is in A. So this would be true if we picked, say, AA or AB, or it's true if we can find something that is equal to A. So yes, this would be true if we pick something like A is equal to A. Then yeah, this is true. But if we pick something like B equals A, this would be false. Or if we pick C equals A, that would be false. So you will see something like X equals A. Remember, it's true if they're the same. It's false if they're different. Okay. One last slide, and we're not gonna worry about this stuff. We're just gonna worry about these equivalents up top. So, sometimes these are taught in like this little box, but we can take these sentences and we can paraphrase these sentences. So on the left, we have everything is P, something is P, not all things are P, and nothing is P. And we can paraphrase these. So one way of saying everything is P, so everything has some property P, is saying that nothing is not P. If everything is P, so let's say everything is happy, that's like saying that nothing is not happy. So all X PX is the same thing as there does not exist an X such that is not PX. Something is P is the same thing as saying that not all things are not P. So if something is a dog, then not all things are not dogs. Something is a dog, not all things are not dogs. If not all things are P, then something is not P. So if not all things are dogs, then something is not a dog. And finally, if nothing is P, then all things are not P. So if nothing is a dog, then all things are not dogs. So we can translate back and forth by taking one of these sentences and doing these manipulations. So in some cases, these are memorized. And by the way, these are not like scope ambiguous sentences where these are different interpretations. These are just paraphrases. So these mean the same thing. Sometimes these are memorized. Of course, there's a little trick to these, So there's two reasons why you might want to know these. So we'll just talk about why we don't use these too often in this course, but they're there for you just in case you want to paraphrase them. One, sometimes it's easier to think of sentences in the alternative form. Nothing is not P. Sometimes you might think of a situation where that happens, and it's just easier in your mind to think of that as everything is P. So if you can translate that, sometimes it's just easier to convert that in your head or on paper. It still takes work to convert it, but sometimes thinking about a paraphrase is easier. Logically as well, if you're working with a formula, sometimes it's easier to do a conversion. In terms of working with sentences as well in tree structures, we'll always use the simpler versions in our trees, but sometimes when you're working with more difficult sentences and tree structures, it's just easier to paraphrase first. Okay, so a trick with these, and it's a nice trick because even though we're using things like existentials and universals in this course, if you take a look at other systems of logic that use things like diamonds and squares and modal logic, um, so things like possibility and necessity, or belief and knowledge, or permission and obligation. So there's many different systems of logic that use different things, or even like time and tense that we'll talk about. The trick works the same with all of these different systems, all of them. We can take a formula like for all x px. So all x px. And we can translate them with just the symbols and pluses and minuses. So whenever we see, in fact, I'm going to space this out a little bit more for all x px. Whenever we see a symbol or a predicate, we just place that down. If we see a negation, we put a minus sign. If we don't see a negation, we put a plus sign. So I would, sorry, sign. So I would write this as plus all plus P. So this is like positive universal, positive P. And now to find the equivalent, what I do is I just change everything except for the predicate. So all the pluses become minuses, all the universals flip to existentials. And then what happens is we end up with an equivalent translation. So this would be minus existential minus P. And if we translate this back into a formula, we get there does not exist an X such that not P of X. And there we have an equivalent translation. So for all X, P of X is the same thing as there does not exist an X such that not P of X. And it doesn't matter what you start with. It doesn't matter what system you use, whether it's diamonds and boxes or what is it, T's and P's in tense systems. This trick will always work for finding equivalent formulas. So you can either memorize the formula, the symbols, you can either memorize or work out the logically equivalent sentences, or you can just work on this little trick to find equivalent well-formed formulas. But no matter which course you take, this is a nice little trick that works. But this can be used for translating sentences as well. Everything is P is the same thing as nothing is not P. Okay, so even this last slide was just a little something I wanted to show you to sort of wrap up the end of predicate logic. There is a little bit more, so we could prove this formally with how this works, but that's a little bit outside the scope of what this version is for. And then we could also do tree interpretations for these, but we're going to do these interpretations with truth conditional meaning of logic. So it'd be kind of like teaching the same thing twice from the ground up. So we'll just end here with predicate logic, and then we'll do the test on Friday. And starting next week, we'll start with formal scope ambiguity. So we'll get to see how we can actually do scope ambiguity in syntactic trees, which is going to blow your mind open if you've never seen 322 material before. if you have seen 322 material, you might be like, oh no, it's movement again. But don't worry, the movement in this course is very relaxed compared to movement in 322. Okay, are there any questions about predicate logic or the upcoming test on Friday? I'm happy to take questions about any of those things. For predicate logic, up to what slide do we need to know for the test? You just need to be able to know whether something is a well-formed formula or not. That is it. So to take a look at a translation and say, is it a woof or not? That's it for predicate logic. There is no lecture on Friday. It's just the test on Friday, but I will be here at 10:20 a.m. and I will be here until 11:20 a.m. So if you want to do it during class time, I'm here to answer questions. So if you think you might have questions or clarification, like anything that you might need me for, and you want to do it during regular class time, I'll be here. Otherwise, you're free to do it anytime between what is it? 9 a.m. and 9 p.m. No, there's no lecture at all on Friday. No content. It's just test. You're doing a test on Friday. It's a 1 hour lecture. I'm not going to make you learn anything when you have a test to do, and that's supposed to be the entire time that's allocated for the course. If there's 1 hour of learning and you have a 1 hour test, I'm not teaching you anything. This is slide 24. Which slide do you actually, or what's the other slide you want? Which content? This one. This one? This one. This one. Other than that, like the actual test questions, everything you need to know is on the test 2 guide on the front page of Canvas. So, yeah. Look over assignment 4 and assignment 3 solutions. They're all in the modules page, by the way, at the top. If you're looking again for assignment 3 and 4 solutions, they're just conveniently located at the top of the modules page. So the predicate logic, so the propositional logic translations, the entailment question, the 2 trees. And you're also able to do the predicate logic practice exercise. So if you want to check whether something is a well-formed formula or not, the predicate logic practice questions have something on that. So if you want to try the practice questions on Canvas, which by the way, do finish up the ones for propositional logic and truth conditional meanings. So those are due as well. But the predicate logic ones have well-formed formula or not practice questions. The first one is one. And all the questions are doable now because the lecture is complete. I will link it on the front page. Will you get our assignment 4 back before Friday? That's my goal. I don't know if I'll achieve the goal, but the goal is to get it back before Friday. I have LING 100 stuff this week that is a lot of work too. So normally I've tried to stagger everything out between the weeks, so that way it's one course or the other, but it's just everything has sort of come together this week as both at the same time. But I will try to get yours back before Friday. The stuff on question 5 is not relevant for this week's test, so I'm not too worried if you don't get 5. Lecture 7 practice exercises are doable now. I'm just putting them on the front page at this point, so that way it's conveniently linked. But yes, it is doable at this point. So that is predicate logic. That is now on the front page. So it's linked there. Okay, I will stop the recording now because it's over time, but if you do have questions, feel free to stick around for a little bit and ask them. But for everyone else, good luck. And I still have office hours tomorrow. Oh, and I have extra office hours on Thursday that I posted in the announcement from 10 a.m. to 11 a.m. So you can also see me there if you have any last minute questions as well.